Hello everyone and welcome to CSCI 343 Fundamentals of Data Science. Today we're going to be talking about images and mathematics. Before we get into that, however, I do want to bring your attention to this. Don't forget, we have a class wiki, and on this class wiki we have notes. Notes that yours truly has spent a lot of time writing to help you get past any questions you might have on any particular topics. So these are going to be really, really helpful for the rest of the semester, all of your assignments. So if you're ever in doubt, check the videos, these guys, look at the slides, but also don't forget about the class notes on the wiki. They're going to be very, very important for your success in the class. Okay, so moving right along. When I was a kid, I loved cartoons so much. And I'm getting reminded, this love I used to have for cartoons when I was a kid. Now that I got a kid of my own, she's watching stuff, her favorite these days is Eleanor Wonders Why. It's like one of her favorite TV shows out there. That and of course things like Daniel Tiger and whatnot. But man, she's singing Eleanor songs constantly these days. Me, I grew up in simpler times. The best on the market back when I was a kid was, of course, the Smurfs. And man, I was a Smurfs fanatic. One of my best memories growing up was when my mom gave me a Smurfs board game. I never, not once, actually played the board game. But I played with all of the parts of that board game so much as a kid. It was ridiculous. But, tying that into what we've got here, kids, they learn by doing things, they learn by playing games, and a fun little game that a lot of kids like to play in their little game books or puzzle books or whatnot is Find the Difference. So how that game works is you have one image side by side with another image, and your task is to try to find what's different from one image to the next. Now, when we do this in person, this is a fun little game, and you're kind of wondering what the heck is this going to lead to. But, humor me here. So, we're going to find a few differences here. Like, the stripes on the bee is different. There's a missing flower. Ooh, he's got a knee patch on this picture, but not in this one. Ooh, there's a missing petal on that rose. In this image, he's looking up at this rose, and this one, he's looking down at that one. And, that's probably most of the differences. There might be one or two more. Let's see. Yeah, we got them all. Fun, right? That was an awesome game. If you're 4 years old, this is no problem for you guys. You're experts at doing a visual analysis of your surroundings. I mean, you're functioning adults, so that's kind of what we have to do. Look for the thing that is out of place. So let's look at this from a different perspective. Let's try to do a more grown-up version of this task. Let's look at this image right here. And I'm going to let you look at this image for a pretty good while. So have a look at it. Memorize what you see here. It's it's not a crazy amount of detail. We've got an aircraft. We've got people boarding an aircraft, right? Okay. So let's take it away for a second and look at it again. Something has changed. Can you see what it is? I'm waiting. Oh, well, you're not here, so you can't really respond. But chances are, because I've done this enough to know, chances are most of you have not noticed what the difference was. But I'm a benevolent virtual overlord. Let's give you another shot. Here's the original image again. So looking back at the original image, can you find what changed? Still nothing? Okay, come on. Okay, we'll do this one more time. By now, some of you have picked up on it, but not many. Chances are probably about 25-30% of you watching have picked up on what the difference was. And for those of you, congratulations. For the rest of you, don't feel bad. This is a hard task to do. It's hard for a plane to take off without, let's back it up, without its engine, right? Look at that. It's there, and now it's not. And that's not a small feature. That's that's in the center of the image, right where your eyes are going to fall naturally. It's a big feature within the image, and it's also a critical feature to the function of what's going to happen in that image. Yet, most of you, including myself when I first saw this, did not catch the difference. And that's because people are actually kind of bad actually sometimes at detecting changes. That's because we expect reality to be somewhat constant. We don't expect plane engines to just pop in and out of existence in the real world. And we can actually take advantage of this in virtual reality. So, of course, me, VR guy, I've got to tie in virtual reality somehow. So we can actually use this as a trick in virtual reality to make you walk around in circles inside of a small room so that you feel like you're walking around a bigger room. So this example here was from a demonstration that we did at USC long ago. Matter of fact, it was designed by this guy here, Evan Sumer Rosenberg. He's at University of Minnesota now. And this demonstration, what would happen is people would walk into a room, and when they walked in the room, behind them, while they weren't looking, a door would change positions. And so they left the room in a different orientation than when they entered the room. So they walk in a room, the door is located like this. While their back's turned, the door flips to the other side of the corner. And then they leave the room 90 degrees from where they walked in. Now I know what you're thinking, because everyone thinks this. Even this guy, the first time he tried this demonstration. There's no way you can fool me with that. I mean, that's a huge difference in the environment. And chances are you're right if you're already familiar with the space. For instance, if we did this trick in like your dorm room or your parents' house or something, you would notice the difference because you have that world committed to memory. But in a world you've never seen before, a novel environment, we can flip doorways around as long as they're not changed too much and you not notice that they happened. So doing this, we could make people walk through this entire little city block here while staying in a physical space as big as that blue square. It's kind of cool, right? So people can be fooled. But again, that was while, our backs were turned. In our little airplane example, we blanked the screen in between one image presentation and the next. And we did that on purpose to sort of give you a mask in between so that you wouldn't directly notice the differences. But let's do something a little bit easier. Let's look at these two images side by side. And if we try to spot the differences, certain things are going to pop out immediately. For instance, the branch over here is obviously missing from this image. There's a person walking on the sidewalk here that's not over here. There's a tower in this image that's not in this image. And that's where the easy ones stop. Turns out, this image is really tricky. There's cracks in the pavement in one image that's not in the other. There's rivets on this metalwork that is in one image and not in the other image. It's pretty darn tricky to find all of the differences. And if you wanted to guarantee 100% that you found every difference in the image, you'd have to sit here and go through it pixel by pixel. So looking at the upper left pixel here versus upper left pixel here versus upper left +1 here, upper left +1 here, and do a pixel per pixel comparison if you wanted to guarantee that you caught every single difference in the image. And that is a tedious task, folks. It's almost as bad as grading assignments. Humans weren't meant to do this. It's torturous. Fortunately, computers are really good at monotonous, repetitive tasks, like checking one pixel versus another pixel. Now, first, we got to ask the question, how does a computer see an image? How does a computer see the world around us? And this image here is foreshadowing what we're going to say. The computer sees the world in a very discrete way. Now, let's look at an example. This is a screenshot of PowerPoint presentation that I do for another class. Matter of fact, it's the first presentation from our virtual reality class, where we talk about the evolution of art. So video games and virtual reality, being an interactive version of art. And so, we've got a picture here, a screenshot of a PowerPoint with a picture in it. Now, if we zoom into a part of this picture, like let's say we select this part right here, we select that, we zoom in, what we see isn't a smooth, continuous image. What we see is something discrete, like little colored Lego snapped together on the screen, little blocks of light. These little blocks of light are called pixels. And if we select one of these pixels and zoom into it further, we find that there are sub-pixels, pixels below the pixels, that are little tiny stripes of red, green, and blue light. And when we vary the intensity of these little subpixels, we can make the pixels appear to be a wide range of other colors. And this is how your computer sees the world. It sees it through pixels. This is effectively a matrix. So if we look at a very simplistic version of this, each pixel has an X position along the horizontal axis and a Y position along the vertical axis. And those pixels are essentially turned on and off in particular ways. So we could represent this little smiley face as a series of ones and zeros in a matrix, where 0 is a pixel that has not been turned on and 1 is a pixel that has been turned on. And this is effectively how computers see the world around us, at least using images. So the cool thing is that images, digital images that we have on a computer, are effectively just plain old normal numerical matrices. There's nothing fancy about them. And the advantage here is this means that we can take numerical analyses and apply them to images in the same way we would apply those same analyses, those same techniques to matrices. So that means we can do nifty things like applying statistics to our image. One of the simplest statistics that you can do to an image is just calculate what's called a difference image. Now, a difference image is effectively taking one image and subtracting another image from it, and then looking at the areas where those two images differed. So if you had two identical matrices and you subtracted them from each other, what would you get out? You would get out another matrix where all of the values are 0. Similarly, if you have an image that's identical to another image, and keep in mind, they're just matrices. If you subtract image 1 from image 2 and they're identical, what should the resulting image be? It should be an image of zeros, and that means a black image. So the values at each pixel in your image is the amount of light contribution at that pixel. So in other words, how bright red is, how bright green is, and how bright blue is. And so if the values in the image are 0, that means the image is very dark, so it's a black image. So if two images are very similar, even if they're not identical, but if they're very, very similar to each other, when you subtract them out, the resulting image should be very, very dark. And so areas where there's a lot of change should be divergent from 0, and areas where there's very little change should converge to 0. So let's take the left image from our previous example and subtract the right image and see what we get. And you'll be amazed at the results. Okay, so here's our left image, our right image. Let's subtract them out, and boom! Wait. What? That's underwhelming. It only found 3 differences. What the heck's going on here, man? I am confused. I'm not really confused. Acting. Anyway, so what happened here? I mean, the first feature that you and I probably saw was this big branch up here at the top of the screen, yet the computer barely found any differences there. Why did that happen? Well, we have to ask ourselves something. So if we're taking this image here, that guy, and subtracting the other image, you can see my pointer up there, I think. Yeah, you can see my pointer. So if we're taking this image and subtracting this image out of it, what would we get like numerically where the branch is? Remember, Darker pixels are closer to zero, so they have smaller values. Bright pixels, on the other hand, have larger values. So when you take a tiny value and subtract a big value from it, what is the result? A negative number. And remember, pixels represent light contribution. Is there such thing as negative light? Well, under normal operating conditions, the universe says no. Which means we had negative values up here because we subtracted bright pixels from dark pixels. And so when we displayed that, we didn't see any difference. There was numerically a difference there, but us, the user, when this was visualized as an image, didn't see a thing. So keep in mind that when you do mathematics with images, you can do mathematics with large values and tiny values and whatnot, but when you display it to the user, it's got to be pixel values that the user can see. So sometimes when you subtract images, you get negative pixels. And there's no such thing as a negative light contribution. So they tend up being shown as just black. So when you do a basic difference image, you're also going to have to take the absolute value of the resulting difference image, preferably in our case using NumPy's absolute value function, to be able to visualize, to see where those differences were. And so if we take the absolute value of that image, on the other hand, we get something that looks like this. And suddenly, all of the tiny differences in the image pop out. Even areas that are probably just a result of differences in image compression. That's a story for another day, though. But all of the large differences, like our branch and our tower and our person, and even the cracks in the sidewalk and the missing rivets, all pop out pretty darn clearly when we do this. And this is a very simple statistic. I mean, it's barely a statistic at all. You're just subtracting two images from each other. So just keep in mind, images are basically numerical matrices. You can do mathematics on images with very little manipulation. And this is sort of the fundamental idea behind image analysis. And there's a lot of places that this is applied. For instance, the researchers over at faceresearch.org look at facial characteristics, so face analysis. And one of the nifty things is they've computed average faces across the world. Kind of cool, right? None of these faces, each of these faces are distinct and unique, and they feel very human to you, but none of them actually exist. These images are the composite of hundreds of faces in each one of these countries averaged together. Cool, right? Now, what does that actually tell us? Well, it can tell us a surprising bit. One, it can give us information about morphological features within a population, but let's talk about this class, for instance. So what we have here is the average image of your faces. Kind of cool, right? What does doing an average tell us? If we think back to our discussion on distributions, our average tells us the center of our population distribution. So it tells us the most frequent features within a population. And the same thing is true of doing statistics on a matrix, or in this case, an image. The characteristics contained within that matrix then represent the most common characteristics within the population of matrices that were averaged together, or in this case, the population of images. So this is from the class roster. All of your faces have been averaged together. This looks like no one in this class, but you do get a very distinct sense of what this person looks like. For instance, the majority of students in this class are Caucasian males. The majority of students in this class have short hair. The majority of students in this class were smiling in their roster photos. And the majority of students in this class were wearing a dark-colored shirt. Mostly sort of like maroony even. Kind of neat, right? So this does not describe individuals in the class, but it does let us see some of the most common characteristics of a population. Now, I'm going to hit on this over and over throughout the course of this semester, and this has to be like the fifth or sixth time I've mentioned it. Our statistics do not describe individuals. Our statistics describe characteristics of populations. So this face, this person, doesn't exist. But this is the average of all of your characteristics put together. Kind of cool, right? So these same kind of characteristics for using analysis to learn and build new things is being applied in a lot of different places. In industry, we're actually seeing new products and structures being developed using machine learning and other analysis techniques. This is sort of beginning to adopt, or this is being adopted in a larger variety of places, and is being called something along the lines of generative design. So, for instance, you can do statistical analysis of structures that have failed or succeeded in some way, or use simulations coupled with like genetic algorithms to design a novel structure or a novel product or a novel whatnot to fit the given parameters of a particular task. So get optimal performance along multiple axes or whatnot. And this is a way of applying statistics to everyday problems. So let's see if we can do something similar without, say, incorporating, like lots of machine learning or genetic algorithms or simulation or anything like that. Let's take something very simple like our image analysis. And I've got a soft spot in my heart for roadster-style vehicles. My favorite, the 1960s, early 70s MGBs. Man, they're not the perfect car, but ain't they pretty? Anyway, and you could fix them with a hammer. They're like go-karts that look nice, pretty much. Anyway, I could talk about that all day. We'll do that another time, though. So here are a few images that I found of, they're not all roadsters, but roadster-like vehicles. I'm defining that as two-seaters, pretty much, that are convertible. And so if we take these 16 images and add them together, well, we add them together and then divide them by 16. So in other words, getting the mean image of all of these vehicles, what do you think we'll get? Kind of exciting thinking about that, right? Can we get an ideal roadster out of these guys? Let's find out. Drum roll. If we average all of these images together, what do we get? We get this. That's not very compelling, is it? It's a blurry image of car? Well, that's frustrating. Well, maybe it's not as frustrating as we think. If we look at the image, we begin to see certain characteristics lining up. So we see something here that's obviously a wheel, another obvious wheel. We see the beginning of an outline of a hood and where the slope of a windshield should be and where a driver's probably sitting, and then a downward slope in the back towards what looks to be a spoiler of some sort, and then maybe a bumper. We were getting details out of this. So let's just do a quick little experiment, trace out the obvious details that we see. And we get an outline that looks like this. Now that isn't bad. That actually looks like a car. And it's all based on the edges of our average image here. So just looking at the edges of our average image, we're able to get something that does, in fact, look a lot like a car out of this. And so I present you with the 2021 Rebel Roadster 343. Brought to you by Motors, of course. No, I'm joking, not really. But the problem here, well, okay, before we get to the problem, let's get to the good thing. The good thing is, using a super basic statistical analysis, just making an average image of a bunch of cars, we're able to generate a profile of something that does, in fact, look like a roadster. And that's new. This isn't exactly like anything we've ever seen, which is where we come to the problem. The more I looked at this after I first taught this, gave this lecture many years ago now, something was bothering me about it. It looked too familiar. It's like, man, I've seen this before. I know I've seen this before. And turns out, it looks remarkably like this vehicle. Amazing! So, it's not exactly like it, but we're actually able to accidentally reproduce a profile that was very similar to a popular roadster. Kind of cool, right? So, excuse me. If we combine what we've learned about difference images and average images, and we do some interesting statistics, we can learn some interesting things about, well, a lot of stuff. One of the examples I like to talk about is analyzing the webcam images from campus. So we've got a webcam site for the campus. You can go and look at camera views of parking lots and in the union and coffee shops and the cafeteria and those kind of things. Now, if you're a sensible person, you check those things in order to see when the line is short at the coffee shop, or when you can run in and get in and out of the cafeteria very quickly, with a bite to eat. But if you're the unreasonable person that obviously someone taking this class is, I'm joking. You're all very reasonable. Uh, you would want to do analysis of these images. So what you can do is you can download updated images from these webcams across campus and then do a change analysis. So if we do a change analysis of this image from the Union, you can probably, for those of you who've been around a while, you can probably tell this is a view from the old Union before we did our renovation. And what we're seeing here is the camera is placed over the entrance to the Union. And we have a busy sidewalk here, then we have the path leading into the Union here, and we see some, well, not surprising stuff. This is the corner where people typically set up booths and tables so they can hand out pamphlets and tell you about this thing or that thing, or give out free samples for something, This is that corner of the Union entrance. And as you can guess, there are people set up handing out pamphlets, talking about the thing that they're passionate about that day, and so naturally there was a lot of activity there. And you can also kind of tell where individuals were standing at this booth. Similarly, you can see that between these two benches, this one gets a lot more activity. Part of that is likely due to the fact that we have an active sidewalk running this way, coupled with the entrance to the Union here. That area sees a lot of activity. People would come and they would sit down, they'd put stuff in that garbage can, they would sit, they would chit-chat with each other, and then move on. And since this is an outside image, we see something beautiful. We see change induced by nature. It's a slightly windy day. So if you look, we see areas of high change. Of course, high change highlighted in red in these images, if you weren't able to tell that already. Areas of high change around the edges of the trees. So the wind was lightly blowing that day, so the branches were slightly swaying, and we could detect that in our image analysis. Now, this is Rebel Market over here. We can get a similarly boring story, or is it? When we look at this image. So here we've got a serving station. We've got another serving station here. This is the entrance, and we see a lot of activity at the entrance to a serving station. The exit is down here. Here's the exit to this serving station. We see a lot of activity coming out. And, not terribly surprisingly, the tables close to the entrance and exits of these serving stations tend to be busier. That makes sense, people coming in and coming out of the serving of the serving booths, going to the closest available table. So not terribly surprising. You can kind of see even like the figures of like individual people like sitting at tables. They're moving around while they're eating their meals and all. So we can see that there's a good bit of activity at the entrance of this one, good bit of activity at the exit from this one. It kind of comes around here, and not surprising. But look at the strange parts. Just like in our Matura example, it's easy to look at the big picture and say, you know what, that looks close enough to what I expect. But always look for the crazy little differences. There's something in here, one little thing, that made me doubt that I even wrote my code properly, and I had to go back and look through the images to figure out what was going on. Notice, we got a little tiny bit of red pixel here, a little tiny bit of red pixel here, red pixels here, a lot of red pixels right here. And it seems like even if there's not a lot of activity at a given table, the middle of the table seems to move. That doesn't make any sense. When I was looking at the analysis, I was like, man, something went wrong. I've got to go debug my code now. Found no problems. If I go back and look at the images, though, we learned something about Rebel Market and their procedures that we did not know beforehand. Periodically, a person comes out of this door that's off screen here and goes and individually checks each one of the paper towel dispensers to make sure that they're full. And that person goes to every single table in this room checking paper towel dispensers. And so what we can draw from this is that it's probably somebody's job to go around and make sure that the paper towel dispensers and probably other things are stocked. And just watching the video feed, it happens so rarely that, it's easy to overlook. But using our image analysis technique, we were able to see that the center of the tables were an area of high activity, even if there weren't people there. And see, that's what you want to get out of a good analysis. You want to find the odd things. Now remember, descriptive statistics like an average image or even a difference image or something like that, is going to tell you the broad strokes of what's happening in your data. It's not going to tell you the fine details. These kind of techniques let you see where there are areas of interesting things happening that you can then go and investigate further. And that's exactly what we're able to get out of this. We're able to take what appeared to be a fairly mundane image and learn things that we actually weren't expecting from our data set. So your next assignment is going to be image analysis. Specifically, we're going to be analyzing images coming from the webcams on campus and looking for areas of high and low activity. And it's going to be exciting. You're going to love it. But you are going to want to read the notes on the website, and I'm going to be posting more information about doing image analysis and image mathematics soon. But a few things to keep in mind. Just like with any other matrix operation, if you're going to be doing matrix math with images, the images have to have the same dimensionality. That means the images have to be the same resolution effectively. This means that you might have to resize your images to get them to mesh up properly. But for your assignment, all of your images are going to be coming from a single camera. You're all going to have different data sets. But your individual data set is going to come from a camera at a given time. And so all the images should be of the same resolution, so you won't have to worry about that. But for future reference, when you're out there working in the wild, doing this for real like a job, always keep in mind that the dimensionality of your images needs to be similar in order for you to do these matrix operations. Another thing, when displaying your images, you want to make sure that the pixel values are typically clamped between 0 and 255. Those are your typical image values or image value ranges for a pixel. If you end up displaying negative pixels, sometimes they won't show up. Sometimes they'll show up as like a randomish color. If you get weird speckledy images, chances are something has gone wrong with the range of pixel values that you're trying to display. So it's usually good practice that when you display your image to make sure that all of your pixels are on the range of values from 0 to 255. And like I mentioned earlier, the values at your pixels while you're doing mathematics on them can be any range that makes sense. You'll end up with negative pixels when doing difference images or whatnot. You can end up with values larger than 255 when adding your images together. Those are okay. But when you go to display your image, if it's looking funky, chances are it needs to be converted to a range of 0 to 255 for all of your pixel values. So always check that. Okay, we're going to wrap up there for today, and if any of you folks have questions, please let us know. Send me or the TA an email, your previous assignment. A good bit of you got in touch with us, which is awesome. That's what we want to see. We want to see you folks getting in touch, asking the questions you have. Because since we're doing this remote, it's difficult to interact with you on a person-to-person level, which, usually when people come up and ask questions at the end of class or something, we don't have those opportunities anymore. So please come to our virtual office hours, send us emails, do whatever, get in touch with us. We're happy to help, and that's what we're here for. So with that said, I hope you all stay happy, healthy, and safe, and see you in cyberspace.